Hello everyone. Now dear student, in this fifth lecture we are going to see the interplanar distances. And we are going to obtain the expression for the interplanar distances. Now dear students, now this figure shows the two-dimensional lattice array. If we connect all these lattice points in any direction, now then there is the formation of the number of the crystalline planes. They are parallel with each other. So the distance between these two planes is known as the interplanar distance. Similarly, in case of that the three-dimensional network, if we imagine the different planes which are parallel with each other, now then the distance between these two planes which are in the lattice structure or the perpendicular distance between the two successive planes of the HKL family, now then that distance is known as the interplanar distances. So simply, in case of that the crystal structure, the number of the planes get oriented in different directions. So it becomes necessary to determine the distance between these two planes, and that is known as the interplanar distances, which is useful for the analysis of any type of the crystalline structure. Now here we are going to obtain the expression of the interplanar distances between the planes. Now for that, consider a simple unit cell in which the three coordinate axes are perpendicular with each other. In this unit cell, consider a plane ABC having the Miller indices HKL. Now let draw a normal from the point O which intersect to the plane ABC at a point N. Therefore, the ON is equal to be the D. This perpendicular distance is known as the interplanar distance. That means there is also the one of the plane at the origin and which is parallel to this plane ABC. So we can consider D is the distance between these two planes. Now let us consider the alpha dash, beta dash and the gamma dash are the angles made by the normal ON to the x, y and the z axis respectively. Then we can find the intercept of the plane ABC corresponding to the three axes, such as the OA is equal to the A by H, OB is equal to be the B by K and OC is equal to be the C by L. Now here the ON is normal to the plane ABC. Then from the geometry of the figure, if we draw a perpendicular line from the point N to the corresponding these three coordinate axes, then we get the one right angle triangle. Therefore, by using this right angle triangle, we can write the cos alpha dash Here, this is, we draw the perpendicular line from this point N to here. So here is the right angle triangle. Therefore, the cos alpha dash is equal to the d divided by the OA. Similarly, in case of that the y-axis, there is the one right angle triangle, and here we can write the cos beta dash is equal to the d divided by the OA. Similarly, corresponding to the z-axis, the cos gamma dash is equal to the d divided by the OC. Therefore, by substituting the value of the OA, OB and the OC in the equation number 2, we get the cos alpha dash is equal to the dH divided by the A, cos beta dash is equal to the dk divided by the B, and cos gamma dash is equal to the dl divided by the C. According to the law of the direction cosines, that is the cos square alpha dash plus cos square beta dash plus cos square gamma dash is equal to the 1. Then by substituting the values of the cos alpha, cos beta and the cos gamma in this equation, we get the t is equal to the 1 divided by under root h by a bracket square, k by b bracket square and l by c bracket square. So here d is the interplanar distance between the two planes. So the HKL are the Miller indices and ABC are the lattice constants. And this expression is known as the interplanar distance between the two planes in any type of the crystalline structure. Dear students, we have seen there are the different systems or the different groups in a Bravais lattice. So take one of the system, that is the cubic system. Now in a cubic system, all the three sides are equal. That is the A is equal to the B is equal to the C. If we substitute these values in the expression of the interplanar distance, so we get the T is equal to be the A divided by the under root h square plus k square plus l square. Similarly, for the another system, that is the tetragonal system. Now in this case, now here only the two sides are equal. If we consider the A is equal to the B, now then we get the expression for the interplanar distance. The T is equal to be the 1 divided by h square plus k square divided by the a square plus 1 upon L divided by the C bracket square. So now in this way, by using this by using the expression for the interplanar distance, we can obtain the interplanar distance for the any system of a crystal structure according to the conditions of the sides of that systems. This is one of the example to determine the spacing between the planes for the FCC structure having the atomic radius 1.75 angstrom unit. The first one is for the plane 100. So here the 100 are the values of the HKL. Now in case of that the FCC crystal structure, the atomic radius is given by the expression R is equal to the A divided by the twice under root 2. Therefore, we can determine the value of A, which is equal to be the twice into under root 2 into r is equal to, we get the 4.95 angstrom. If we substitute the value of the A and the values of the Miller indices, we can determine the interplanar distance corresponding to the plane 100 equal to the 4.95 angstrom unit, and corresponding to the plane HKL plane 200, the value of the D is the 2.48 angstrom unit. So with the help of the expression of the interplanar distances, we can determine the value of D for the any system in case of that the crystalline structures. Now I am thankful to all of